Far out beyond the orbit of Neptune, drifting in the cold, dark reaches of our solar system, there exists a world so mysterious that astronomers still struggle to understand its secrets. This is Orcus, a dwarf planet hiding in the Kuiper Belt, a realm of icy objects that holds clues to the very formation of our cosmic neighborhood. Despite being discovered more than 2 decades ago, Orcus remains one of the most enigmatic bodies in our solar system, a ghostly world that challenges everything we think we know about distant planetary objects. Its strange orbit, puzzling composition, and unexplained features have captivated scientists and space enthusiasts alike, drawing us deeper into questions about what lies at the edge of our celestial backyard. What makes Orcus especially intriguing is how it defies simple categorization. It's not just another frozen rock in the dark. It possesses characteristics that seem almost contradictory. For instance, it has its own moon, Vanth, which circles it in a dance that raises questions about gravitational capture and formation history. Its surface reflects light in ways that suggest the presence of materials science can't yet fully explain, while its size and shape hint at a complex and violent past. Some researchers even speculate that Orcus might be a key to understanding planetary migration, the great reshuffling that occurred billions of years ago as the giant planets settled into their current orbits. Each mystery pulls us further into the story of this distant dwarf planet, inviting us to explore the unknown. In this video, we're going to journey through 25 of the most compelling unexplained mysteries surrounding Orcus. From its peculiar resonance with Neptune to the possibility of hidden geological activity on its frozen surface, we'll uncover why this world continues to fascinate and baffle those who study it. You'll discover how something so far away can feel deeply connected to the story of our own planet, and perhaps even catch a glimpse of what future missions might reveal when we finally send a probe to this distant outpost. So settle in, open your mind to the wonders of the cosmos, and prepare to explore the enigmatic dwarf planet Orcus, a world that reminds us just how much we have yet to learn about the universe we call home. Our first great puzzle takes us to the very path Orcus carves through the void. This distant world is locked in an intricate gravitational dance with the ice giant Neptune, a relationship that is both familiar and profoundly strange. Like Pluto, Orcus is in what is known as a 2 to 3 orbital resonance with Neptune. For every 2 trips Neptune makes around the Sun, Orcus completes 3. This rhythmic celestial choreography means that whenever Orcus and Neptune approach each other, they are always in the same relative positions, creating a stable, repeating pattern that prevents them from ever getting too close and avoids a catastrophic gravitational encounter. But here is where the mystery deepens. While Pluto's resonance is well understood as a protective mechanism, the specific details of Orcus's orbit present a series of head-scratching anomalies. Its orbital stability is almost too perfect, exhibiting a level of precision that current models of the early solar system struggle to fully account for. How did this specific dwarf planet, out of countless others in the Kuiper Belt, achieve and maintain such a perfectly tuned relationship with a giant planet over billions of years? The forces at play during the solar system's violent formative period were chaotic, a gravitational tug of war that should have scattered orbits, not polished them to such a fine degree. Furthermore, the exact parameters of its path hold peculiarities that defy simple explanation. The tilt of its orbit, its eccentricity, and the specific angles of its approach to Neptune all contain small but significant deviations from what theoretical predictions suggest they should be. These aren't random fluctuations, they are consistent quirks, hinting that something is missing from our equations. Perhaps the gravitational influence of another unseen, larger object in the far reaches of the solar system has subtly sculpted its path. Or maybe the initial conditions of its formation were so unique that they imprinted this specific, stable signature on its journey around the Sun. Unraveling the story of Orcus's orbit is more than an academic exercise. It is a direct line back to understanding the dynamic and tumultuous processes that built our planetary neighborhood and left behind this perfectly balanced yet deeply puzzling cosmic clockwork. Moving from the gravitational dance that defines its path, we encounter a second, perhaps even more fascinating mystery: the intimate relationship between Orcus and its solitary moon, Vanth. Most large objects in the Kuiper Belt have companions, but the Orcus-Vanth system is an outlier that stands out for its sheer peculiarity. The most striking feature is their size ratio. Vanth is unusually large for a moon of a dwarf planet. Estimates suggest it could be nearly a third the diameter of Orcus itself. This is not a small rock orbiting a giant world. This is far closer to a binary system, a pair of cosmic siblings dancing together in the dark. For comparison, our own moon is about a quarter of Earth's diameter, a ratio we consider substantial, but out in the Kuiper Belt, such a proportion is almost unheard of. Charon, Pluto's largest moon, is about half of Pluto's size, making that system a true binary where both bodies orbit a point in space between them. Orcus and Vanth, however, don't quite reach that extreme, leaving them in a strange and unique category all their own. This unusual size difference immediately raises a profound question about their origin. How did this pair come to be? The leading theory for moon formation around these distant bodies involves a massive impact, much like the giant impact hypothesis that created Earth's moon. A colossal collision in the early solar system could have blasted material into orbit that later coalesced to form Vanth. Yet, the mechanics of such an event creating a moon this large and in such a stable orbit are difficult to model. The energy required would be tremendous, and the resulting debris field might have created multiple moons or a ring system, not one single large companion. The alternative theory is gravitational capture, that Orcus and Vanth formed separately and were later drawn together, but this too is a problematic explanation. The Kuiper Belt is vast and mostly empty. The chances of two large objects passing close enough for a gentle capture without a catastrophic collision or being flung away by gravitational forces are astronomically low. Vanth's nearly circular orbit around Orcus adds another layer of complexity, as a captured object would typically be expected to have a much more elliptical or irregular path. The orbital characteristics themselves are a source of deep intrigue. Vanth orbits Orcus at a distance that seems almost too perfect, and its orbital period is synchronized in a way that suggests a long, stable, and quiet history. There's no detectable wobble or precession that would point to a violent recent past. This serene dynamic is completely at odds with the chaotic, impact-filled environment we believe the early Kuiper Belt possessed. It's as if we are looking at a system that has been utterly undisturbed for billions of years, a frozen snapshot of a relationship formed in the solar system's infancy. Furthermore, spectroscopic observations reveal that the surface composition of Vanth is distinctly different from that of Orcus. Orcus appears to be covered in water ice, while Vanth's surface is darker and likely contains a higher proportion of complex organic compounds or tholins, giving it a much redder hue. This compositional difference is a critical clue. If both bodies formed from the same material after a single impact, why do their surfaces look so different? Were their evolutionary paths separate for a long time before they became a pair? Each observation deepens the mystery, transforming this binary system from a simple footnote into a central puzzle that challenges our fundamental understanding of how celestial relationships are forged in the frozen depths of our solar system. But the enigmas of this distant world extend far beyond its orbital dance and its puzzling partner, drawing our attention directly to its very surface. As we turn our most powerful telescopes toward Orcus, analyzing the faint light it reflects, we are met with a spectral signature that is both dazzling and deeply confusing. This third great mystery revolves around the composition of its frozen exterior, a puzzle written in ice and light that challenges our expectations of what a Kuiper Belt object should be. Most denizens of this remote region are relatively dark, their surfaces weathered and darkened by billions of years of cosmic radiation, their ices primordially ancient and simple. Orcus, however, presents a far more complex and vibrant picture. The most prominent and surprising feature is the sheer abundance and crystalline structure of water ice detected on its surface. This isn't just any ice, it is ice in a highly ordered crystalline form. This is significant because in the frigid environment of the Kuiper Belt, where temperatures hover just a few dozen degrees above absolute zero, water ice should naturally exist in a more amorphous, disordered state. The presence of a crystalline structure strongly suggests that this ice has been recently processed or somehow rejuvenated. It implies that the surface of Orcus has either been heated or actively reshaped within a cosmically recent time frame. But what could be the source of this energy? Orcus is far too small to possess any significant internal radioactive heating, and it receives virtually no warmth from the distant sun. The leading theories are as fascinating as they are speculative. Perhaps Orcus experienced a period of tidal heating generated through gravitational interactions, possibly with Vanth during a closer orbital past. Maybe it was struck by a sizable object, an impact that generated enough localized heat to melt and recrystallize vast expanses of ice. Or, most intriguingly, could this be evidence of cryovolcanism, the eruption of water, ammonia, or methane ices from a potentially liquid subsurface ocean, a process that would instantly refresh the surface with new crystalline material? Each possibility points toward a world that is not a static, frozen relic, but one that may still be geologically dynamic in ways we are only beginning to imagine. Complicating the picture further are the tantalizing hints of other compounds mixed with this bright water ice. Spectral data suggests the potential presence of ammonia hydrates, a combination that acts as a potent antifreeze. The existence of such a substance could dramatically lower the melting point of subsurface ices, making the possibility of a hidden, slushy ocean or occasional cryovolcanic flows far more plausible. Even more intriguing are the darker, reddish patches that mottle the otherwise bright surface. These regions are likely rich in complex organic molecules known as tholins. These are not signs of life, but rather the result of simple carbon-containing compounds like methane being bombarded by cosmic radiation over eons, a process that creates a dark, reddish-brown, tar-like sludge. Tholins are common on many Kuiper Belt worlds, but on Orcus, their distribution is patchy and uneven, concentrated in specific areas rather than forming a uniform blanket. This uneven distribution suggests a surface that is actively being altered. Perhaps cryovolcanic plumes are depositing fresh, bright ice in some regions, while the relentless rain of radiation darkens older, undisturbed terrain elsewhere. It creates a portrait of a world with its own active geological cycle, a slow mutation of ice and organics that is utterly alien to our terrestrial experience. What makes Orcus truly stand out, however, is that when you take all of this data together, the crystalline water ice, the potential ammonia, the patchy tholins, it doesn't cleanly match the spectral profile of any other major Kuiper Belt object. It's not a near twin of Pluto, which has vast plains of nitrogen ice and a complex, layered atmosphere. It doesn't perfectly mirror the composition of Haumea, which is almost entirely crystalline water ice due to a gargantuan ancient impact. It occupies a unique compositional niche all its own. This spectral uniqueness forces us to confront the possibility that Orcus formed under very specific and unusual conditions, perhaps in a different region of the early solar system before being gravitationally flung into its current orbit during the Great Planetary Migration. Its surface is not just a random assortment of ices, it is a preserved record of its origin and subsequent history. Decoding that record is like trying to read a book in a language we don't fully understand, each page offering clues to a story of formation, migration, and perhaps even hidden activity, written in the complex chemistry of its frozen, alien landscape. And just when we think we have a handle on the general composition of this distant world, a specific and startling feature comes into focus, pulling us into our fourth great mystery. High-resolution observations from the most advanced ground-based telescopes and the Hubble Space Telescope have revealed something that shouldn't be there: an intensely bright albedo feature, a spot of light so reflective it stands in stark contrast to the darker, reddish terrain surrounding it. This isn't a subtle variation, it is a brilliant anomaly, a beacon on the surface of Orcus that defies easy explanation. In the perpetual twilight of the Kuiper Belt, where sunlight is over 1,000 times fainter than on Earth, such a vivid patch of brightness is more than just unusual, it is a direct challenge to our models of these frozen worlds. The immediate and most plausible scientific explanations point toward dramatic geological processes. The leading candidate is cryovolcanism. Imagine not a volcano spewing molten rock, but one erupting with a frigid slurry of water ice, ammonia, and methane. If a subsurface ocean or a localized pocket of liquid exists beneath the icy crust, the tremendous pressure could force this material to the surface in a brilliant, slow-motion eruption. As this slushy mix spread across the terrain and instantly flash froze in the vacuum of space, it would create a vast, new, and incredibly reflective plane of pristine ice, effectively painting a bright spot on the planet's face. This would perfectly account for the crystalline water ice signature we see and tie directly into the previous mystery of its surface renewal. Another compelling natural theory involves a recent impact. A sizable object slamming into Orcus could have done two things. First, the energy of the impact would have generated enough heat to melt existing surface ices, which then refroze into a smooth, glassy, and highly reflective sheet. Second, and perhaps more likely, the impact could have simply excavated fresh, clean ice from beneath a dark, radiation-processed surface layer. For billions of years, cosmic radiation has been bombarding Orcus, slowly cooking its surface ices into the dark, reddish tholins we see. If an impactor punched through this ancient, darkened crust, it would blast it away, revealing the bright, untouched ICE Chinese letter below, creating a brilliant new crater akin to a fresh wound on the dwarf planet's surface. Yet, the extreme and localized nature of this bright spot has perhaps inevitably spurred more speculative ideas. In the realm of pure scientific conjecture, some have wondered if we are seeing evidence of something entirely novel, a form of geology we haven't yet conceived of, unique to the pressure and temperature regimes of these distant objects. Could exotic ices with different crystalline structures or light-scattering properties form under these conditions? And in the farthest reaches of imagination, the concept of artificiality is occasionally floated, not as a serious proposal but as a testament to how profoundly puzzling this feature is. It serves as a reminder that when confronted with the truly unknown, the human mind explores every possibility, no matter how remote, highlighting that this bright spot is one of the most visually compelling and least understood features in the entire outer solar system. Ultimately, this enigma may only be solved by getting a closer look. The bright spot remains a primary target for any future mission to the Kuiper Belt. Is it a frozen cryovolcanic flow, a brilliant impact crater, or something even more unexpected? Its existence transforms Orcus from a fuzzy, distant world into a specific destination, a place with a landmark that calls out for exploration, representing a tantalizing piece of a puzzle that we are only beginning to assemble. While the brilliant white spot captures our attention visually, the mysteries of Orcus extend into an invisible realm, revealing puzzles that are felt rather than seen. Our fifth great mystery takes us from the reflected light of the surface to the very heat it emits, uncovering a thermal profile that defies all logical expectation for a world so far from the sun. In the profound cold of the Kuiper Belt, where the sun is little more than an exceptionally bright star, temperature should be almost uniform. The primary source of warmth is solar radiation, and at that distance, its effect is minimal and predictable. An object like Orcus should be a nearly uniform ball of deep cold, with only slight, predictable variations between the areas facing the sun and those in shadow. Yet, when astronomers measured its thermal emissions, they found something entirely different: a patchwork of unexpected hot and cold spots, a bizarre and irregular temperature map that simply cannot be explained by sunlight alone. This thermal inconsistency presents a profound challenge. If the distribution of heat doesn't align with solar exposure, then something else must be actively regulating the surface temperature. One compelling possibility is the presence of a transient, ultra-thin atmosphere. On worlds like Pluto, the slow sublimation of surface ices, where solid turns directly to gas, can create a temporary atmosphere that redistributes heat across the globe. Perhaps on Orcus, pockets of highly volatile ices like methane or nitrogen are warming in fleeting sunlight, turning to gas and carrying thermal energy to other regions before collapsing back onto the surface as frost. This process could create localized warm areas where sublimation is active and colder spots where the gas recondenses, effectively creating a breath-like cycle of atmospheric puffing that would continuously reshuffle the thermal deck. However, directly detecting such a wispy, intermittent atmosphere with our current technology is nearly impossible from Earth, leaving it a tantalizing but unproven hypothesis. The more dramatic explanation points inward toward the dwarf planet's core. Could Orcus possess a source of internal heat? For a small, rocky, icy body billions of years old, this seems counterintuitive. The heat from its initial formation should have dissipated eons ago, and it is too small to host significant long-lived radioactive elements that keep Earth's interior hot. But other mechanisms could be at play. Tidal heating generated by the gravitational pull of its large moon Vanth could provide a steady internal energy source. If their orbit has changed over time, moving through periods of greater eccentricity, this gravitational friction could have warmed Orcus's interior, much like the forces that power the volcanic moons of Jupiter. This residual heat could then slowly seep to the surface through cracks and fissures, creating localized warm spots and potentially even sustaining a subsurface ocean, further fueling the possibility of cryovolcanic activity that we see evidence for elsewhere. Another fascinating angle involves the surface composition itself. The bizarre thermal map might be a direct consequence of the strange mix of materials we see. Different substances absorb and radiate heat at vastly different rates. A patch of dark, reddish tholin-rich terrain would absorb more of the feeble sunlight than a neighboring area of brilliant white water ice, which would reflect most of it away. This could create a situation where a dark patch becomes slightly warmer than its bright surroundings, even if both are receiving the same amount of solar energy. This process, known as thermal inertia, could account for some variation, but the scale and intensity of the temperature differences observed on Orcus suggest that composition alone is not the full story. It appears that an active process is continually refreshing this thermal landscape, preventing it from reaching the dull, uniform equilibrium we would expect. Ultimately, these temperature irregularities paint a picture of a world that is not the static, frozen corpse we once imagined Kuiper Belt objects to be. Instead, Orcus emerges as a potentially dynamic body, where internal forces, atmospheric whispers, and complex surface chemistry interact in a delicate and unseen ballet of heat and cold. This thermal mystery is deeply interconnected with all the others. The same internal heat that could explain the warm spots might also power the cryovolcanism that creates the bright, reflective plains and keeps the water ice in a crystalline state. It suggests we are not looking at a simple ball of ice and rock, but a complex planetary body with its own hidden energy budget and active geology. operating on a slow, cosmic timescale in the silence of the solar system's deepest frontier. Yet, the strange perfection of this resonance only deepens the puzzle because the gravitational story of our solar system is one of chaos, not clockwork. The early days were a violent ballet, a period known as the Late Heavy Bombardment, where the giant planets are believed to have migrated, their shifting gravity scattering countless icy bodies inward and outward like cosmic billiard balls. In such a tumultuous environment, delicate orbital relationships should have been shattered, not perfected. So how did Orcus not only achieve this precise 2 to 3 rhythm, but also maintain it with such unwavering stability across 4.5 billion years? This persistence suggests there is a hidden layer of subtle gravitational engineering at work, a set of forces we have yet to fully account for in our models of the outer solar system. One compelling possibility is that the resonance is actively maintained by the cumulative gravitational influence of the other countless objects within the Kuiper Belt itself. While individually small, the combined mass of these innumerable icy bodies could create a gentle, background gravitational field that acts as a stabilizing force, a kind of cosmic gyroscope that subtly corrects any tiny deviations in Orcus's path, nudging it back into its perfect rhythm with Neptune. This would mean Orcus is not dancing alone with the giant planet, but is part of a vast, synchronized chorus, its motion fine-tuned by the whispers of 1,000 unseen partners. An even more speculative and thrilling theory points to the potential influence of a much larger, yet undiscovered, mass in the far outer solar system, the hypothesized Planet 9. This proposed super-Earth, lurking far beyond Pluto, would possess a gravity powerful enough to shepherd the orbits of many distant objects. It's conceivable that the same gravitational influence that clusters the orbits of extreme trans-Neptunian objects is also providing a periodic tug on Orcus, acting as a metronome that helps keep its resonant timing with Neptune impeccably precise. The orbit of Orcus could thus become a key piece of evidence in the ongoing hunt for this potential new planet, a clue written in the silent motion of a distant dwarf world. Ultimately, the resonance of Orcus is more than a celestial curiosity. It is a preserved record of the solar system's most dynamic era. Its unwavering timing suggests that the processes which sculpted our planetary neighborhood were not entirely random, but included mechanisms of astonishing fine-tuning. By studying the nuances of this gravitational dance, we are essentially reading a history book of the solar system's youth, a history where the gentle, persistent forces of gravity carved out pockets of perfect order within the primordial chaos, leaving behind a resonant world as a testament to that forgotten era of cosmic creation. Shifting our focus from the grand scale of orbits to the intimate spin of the world itself, we arrive at a seventh enigma that is both subtle and profoundly telling, the curious case of how Orcus rotates. Every celestial body pirouettes through space, and the specifics of that spin, its speed, and the tilt of its axis act as a frozen record of its history, preserving the memory of ancient impacts, gravitational encounters, and internal shifts. For a typical Kuiper Belt object of its size, we would expect a certain range of rotational behaviors, a kind of standard rhythm to the cosmic dance. Orcus, however, moves to a beat all its own, its rotation period and axial tilt presenting clear anomalies that point toward a dramatic and turbulent past. The most immediate puzzle is its rotation speed. Current estimates suggest Orcus completes a full turn on its axis roughly every 10 hours. While that might not sound unusual at first, it becomes deeply interesting when compared to its closest cousins in the distant solar system. Other large trans-Neptunian objects like Pluto, Haumea, and Eris have rotation periods that cluster within a similar range, but they often have clear and dramatic reasons for their spin. Haumea, for instance, spins with a dizzying velocity, completing a rotation in under 4 hours, a frenzy believed to be the direct result of a colossal impact that shattered its original structure and sent it tumbling wildly. Orcus, by contrast, occupies a middle ground. Its 10-hour day is not exceptionally fast, but it is faster than what would be expected for a pristine, undisturbed body that slowly coalesced from the primordial cloud. This moderate yet unexpectedly quick spin hints that something gave it a significant push, a gravitational nudge or a substantial collision that imparted angular momentum, speeding it up without sending it into a full-blown rotational frenzy. This leads directly to the question of what could have caused such a push. The prime suspect is a massive impact in its deep past. A collision with another sizable Kuiper Belt object could have transferred a tremendous amount of rotational energy, setting Orcus spinning at a new, faster rate. The fact that it has a large moon, Vanth, adds compelling weight to this theory, as such an impact could have simultaneously created the moon and altered the dwarf planet's rotation, a two-for-one cataclysm that would explain two major mysteries with a single event. However, the mechanics are not perfectly clear. For an impact to create a moon as large as Vanth and leave Orcus with its current, moderately fast spin requires a very specific angle and velocity of impact, a celestial strike of incredible precision. The alternative explanation involves gravitational interactions. During the solar system's early days, when large bodies passed much closer to each other, a near miss with another massive object could have gravitationally torqued Orcus, pulling on it and effectively revving its engine like a gravitational slingshot. Over millions of years, the subtle tidal tug from its moon Vanth could also have played a role, slowly altering its spin rate until it settled into its current rhythm, a process known as tidal locking, though Vanth itself is not locked to Orcus in a mutual embrace, adding another layer of complexity to their relationship. Perhaps even more puzzling than its rotation speed is the tilt of its axis, its obliquity. This is the angle between its rotational axis and the perpendicular to its orbital plane. Earth, for example, has a tilt of about 23.5 degrees, which gives us our seasons. Many Kuiper Belt objects have significant axial tilts, but Orcus's is particularly extreme, estimated to be very large, potentially even approaching a 90-degree roll where its poles point almost along its orbital path. Such an extreme tilt is a glaring signpost pointing to a violent history. A planet doesn't just decide to roll over on its side. An enormous amount of force is required to completely reorient its entire structure. This is not a gentle process. A tremendously powerful impact could have literally knocked the world sideways, or the cumulative gravitational influence of the giant planets during their great migration billions of years ago could have gradually but powerfully torqued its axis into its current tipped-over position. What makes the rotational dynamics of Orcus so critical to understanding its story is that they are not separate from the other mysteries we've explored. They are deeply intertwined. The same colossal impact that may have created Vanth and sped up its rotation could also be the source of the internal heat that keeps its water ice crystalline and potentially fuels cryovolcanism. The extreme axial tilt would have a profound effect on its climate and geology, creating wildly varying seasons that last for centuries, where one pole is bathed in continuous sunlight while the other is plunged into deep frozen night. This could drive the sublimation and redeposition of surface ices, contributing to the patchy thermal and compositional variations we detect from Earth. The rotation of Orcus is not just a simple fact, it is the key that connects the story of its formation, its internal activity, and its surface appearance, a single thread woven through the entire tapestry of its existence, revealing a world shaped by monumental forces in the solar system's violent dawn. But the challenges of observing this distant world extend beyond its spin and into the very fundamentals of its physical presence, leading us directly into an eighth great mystery: the perplexing and ongoing debate over the most basic properties of Orcus, its size and its mass. For any celestial body, these are the foundational metrics, the essential numbers that allow us to categorize it, understand its density, and speculate about its composition and internal structure. With most objects, astronomers arrive at a consensus relatively quickly, but Orcus resists such easy categorization, presenting us with conflicting data that stubbornly refuses to align. Depending on the observation method used, Orcus appears to be different sizes and possess different masses, a discrepancy that points either to a series of frustrating measurement errors or to a genuinely unique physical property that is skewing our perception of this distant world. The primary methods for sizing up a distant Kuiper Belt object are direct imaging and occultations. Direct imaging, often using the incredible resolving power of the Hubble Space Telescope, allows astronomers to measure the object's angular diameter, how large it appears in the sky. Combined with a precise measurement of its distance, this gives a direct calculation of its physical size. Meanwhile, an occultation occurs when Orcus passes in front of a distant star, briefly blocking its light. By meticulously timing the duration of this stellar dimming from multiple observation points on Earth, scientists can trace the silhouette of Orcus and get an extremely accurate measurement of its width at that specific moment. The problem is, these two methods have not always agreed. Some early direct measurements suggested a larger diameter, while occultation data sometimes points to a slightly more compact world. Even tiny differences of several dozen kilometers are significant, as they dramatically alter the calculated surface area and volume, which are critical for all subsequent analysis. The plot thickens considerably when we bring mass into the equation. The mass of Orcus is not measured directly by looking at it. It is calculated by observing the orbital dance of its moon, Vanth. By applying Newton's laws of motion to Vanth's orbit, measuring its orbital period and the distance between the two bodies, astronomers can calculate the combined mass of the entire Orcus-Vanth system with a high degree of precision. Once they estimate Vanth's mass based on its size and assumed density, they can subtract it to find the mass of Orcus itself. This is where the real contradiction emerges. When you take this well-defined mass and divide it by the volume calculated from the smaller size estimates, you get a surprisingly high density. This would suggest a world that is very rocky with a relatively thin mantle of ice. However, if you take that same mass and divide it by the volume from the larger size estimates, the calculated density plummets, suggesting a much icier, less dense, and more porous body, something more like a fluffy snowball than a rocky planetesimal. This density disagreement is far from an academic squabble. It strikes at the heart of what kind of world Orcus is. A high-density Orcus would imply it formed in the warmer, inner solar system near the giant planets, where stronger sunlight blew away lighter ices, leaving behind a rockier composition. It would then have been gravitationally scattered outward to its current home in the Kuiper Belt. A low-density Orcus full of pristine ice would suggest it formed right where it is, in the cold outer solar system, and is a more primordial, unchanged relic of the solar nebula. We are looking at two completely different origin stories based on a difference of a few kilometers in measurement. So what could be causing this fundamental disagreement? One possibility is simple observational error. Measuring the precise size of a faint, pixelated object 4 billion miles away is arguably one of the most difficult tasks in astronomy. Imperfect optics, atmospheric interference, and the inherent challenge of determining where the faint edge of a fuzzy world truly ends can all introduce small but critical mistakes. Perhaps we simply need better data from a future flagship telescope or a dedicated interstellar mission. The more thrilling possibility is that the discrepancy is real and is caused by a physical property of Orcus itself that we haven't fully accounted for. Perhaps its surface is so incredibly porous and fluffy, like a fractal layer of snow, that it doesn't present a hard, definitive edge to occulting stars. Light from the background star might dim gradually as it passes through this tenuous outer layer, making the world appear larger in an occultation than it truly is. Alternatively, Orcus might be slightly oblong, not a perfect sphere, and we are seeing it from different angles during different observations, each giving a different measurement of its apparent girth. Or its astonishingly bright and dark surface patches could be fooling our instruments. A brilliantly reflective spot can make an area appear larger and more prominent in direct imaging than a dark, non-reflective region of the same actual size. Untangling this mystery is paramount because until we know its true size and mass, we cannot know its density. And without knowing its density, every other mystery remains unsolved. We cannot confidently model its internal structure, understand whether it can support a subsurface ocean, or accurately reconstruct the impact that created Vanth. The size and mass of Orcus are the keystone numbers that hold up the entire arch of its story. This ongoing debate is a humbling reminder that even in an age of advanced technology, the most basic truths about our solar system's farthest worlds remain just out of reach, waiting for a sharper image or a closer look to finally bring them into focus. Adding another layer to the surface puzzle, we encounter the ninth mystery, the strange and stubbornly unidentifiable nature of the dark material itself. While we've already noted the presence of dark, reddish patches that contrast with the bright water ice, the real enigma lies in the detailed chemical signature of this material. When astronomers point their spectrometers at these regions, they receive data that simply doesn't match the profile of any known compound we'd expect to find. It possesses the ruddy hue typical of tholins, those complex organic polymers created when solar radiation bombards simple molecules like methane, but its spectral fingerprint is off. The specific way it absorbs and reflects light contains anomalous bands and features, suggesting that the recipe for this cosmic tar is far more exotic than anything we've catalogued elsewhere in the solar system. This presents a fascinating chemical conundrum. The environment of the Kuiper Belt is, in theory, a fairly standard laboratory for this kind of chemistry. Ultraviolet light and cosmic rays should be slowly processing the same basic ingredients, frozen methane, nitrogen, carbon monoxide, into the same basic tholin-like end products we see on Pluto, Triton, or Makemake. But on Orcus, the process seems to have taken a different turn, yielding a substance with a unique molecular configuration. One compelling theory is that the unique thermal environment of Orcus is directly influencing the chemistry. The potential internal heat and the bizarre temperature variations we discussed could be providing just enough energy to catalyze different chemical pathways, guiding the formation of more complex or differently structured organic molecules than those formed in the utterly cold, static environments of its neighbors. It's the difference between a slow, cold cure and a slightly warmer, more active bake, resulting in a completely different final product. Another possibility is that the starting ingredients were different. Perhaps the ices on Orcus contained a rare mixture of compounds, such as acetylene or hydrogen cyanide, that are less common on other Kuiper Belt objects. When irradiated, these precursor molecules could polymerize into a form of tholin that is structurally unique, with different bond types and light-absorbing properties. There's also the potential role of its large moon, Vanth. If the two bodies have exchanged material through impacts, Vanth's own distinct surface composition, which is notably darker and redder than Orcus's, could have deposited foreign matter onto the dwarf planet, creating localized patches of an imported, and thus unfamiliar, type of dark material. The most profound implication of this mystery is that we might be looking at an entirely new class of material, a substance forged in conditions so specific to Orcus that it doesn't exist anywhere else we've yet observed. This wouldn't be a mere variation on a theme. It would be a whole new chapter in planetary chemistry. It suggests that the outer solar system, far from being a monotonous expanse of similar icy worlds, is a place of incredible chemical diversity where slight differences in location, history, and internal composition can lead to dramatically different outcomes. Unlocking the secret of this dark material is therefore about more than just understanding one dwarf planet. It's about expanding our entire vocabulary of cosmic chemistry and discovering new processes that may be at work on countless unseen worlds throughout the galaxy. The story of how Vanth came to orbit Orcus is a cosmic detective story with multiple conflicting suspects and no clear culprit, making its origin our 10th great mystery. The most widely accepted theory for moon formation across the solar system is the giant impact hypothesis. This violent and spectacular process is how we believe Earth's moon was created, and it neatly explains the existence of Charon, Pluto's large moon. The idea is straightforward. In the chaotic early solar system, a massive object, perhaps another sizable Kuiper Belt object, slammed into a young, still-forming Orcus. This catastrophic collision would have blasted a tremendous amount of debris into orbit around the wounded dwarf planet. Over time, this ring of shattered rock and ice would have coalesced under its own gravity, eventually forming the moon we now call Vanth. This theory is compelling because it simultaneously explains two things: Vanth's existence and its substantial size. A colossal impact could easily have ejected enough material to form such a large companion. Furthermore, if the impactor itself was rich in different materials, it could account for the puzzling compositional differences between the water-ice-dominated Orcus and the darker, potentially Tholen-rich Vanth, as the moon would have formed from a unique mixture of material from both bodies. However, for all its elegance, the giant impact scenario faces some serious challenges when applied to this specific pair. The primary issue is the remarkable stability and near-perfect circularity of Vanth's orbit. A moon born from the debris of a violent collision would typically be expected to have a more eccentric or elliptical path as the leftover material settled into a stable configuration. Vanth's orbit, by contrast, is almost perfectly circular, which suggests a much gentler and more orderly birth. Furthermore, sophisticated computer simulations of such an impact struggle to produce a system that looks exactly like Orcus and Vanth, generating a moon that is 1/3 the size of its parent, while leaving the parent itself with a moderately fast rotation and not completely shattered, requires an impact of incredibly specific force and angle, a celestial bullseye that, while not impossible, seems statistically improbable. The impact theory leaves lingering questions about why the system appears so serene and perfectly balanced if its origin was one of unimaginable violence. This has led scientists to seriously consider the alternative, gravitational capture. In this scenario, Orcus and Vanth began their lives as independent objects, two separate dwarf planets or large planetesimals orbiting the Sun in the crowded early Kuiper Belt. Through a complex gravitational dance, they passed close enough to each other that Orcus's gravity ensnared Vanth, pulling it into a permanent orbit. This would explain their different compositions perfectly, as they would have formed in different parts of the primordial disk, accumulating vastly different types of ice and rock. The capture theory gets around the problem of having to explain a perfect impact, but it introduces an even greater statistical improbability. The Kuiper Belt, both now and in the past, is an overwhelmingly empty place. For two specific, large objects to pass close enough for a gentle capture without either colliding and annihilating each other or gravitationally flinging one another out of the solar system entirely requires a set of initial conditions so precise it borders on the miraculous. It would be like throwing two needles into the ocean from different continents and having them somehow find each other and link together. For capture to be viable, there likely had to be some additional mechanism at play, such as a drag force from a denser primordial solar nebula or a complex three-body interaction where the gravity of a third object helped bleed off enough energy to allow the capture to happen. The failure of these two standard models to provide a completely satisfactory answer has given rise to a third, more unusual possibility, a hybrid origin story. Perhaps Vanth is not a single captured object, but the remnant core of a much larger body that was mostly destroyed in a glancing blow with Orcus. In this scenario, a proto-Vanth was struck and shattered, with most of its icy mantle being stripped away and lost to space, while its dense, rocky core survived and was captured by Orcus's gravity. This could account for its relatively high density compared to Orcus if measurements hold, merging the violence of an impact with the mechanics of a capture. Another fringe but fascinating idea is that Vanth represents a truly primordial type of object, a surviving member of the initial population of building blocks that formed the solar system, which Orcus gathered and held onto as a permanent gravitational trophy from the dawn of time. Each theory has its merits and its flaws, and the truth is that with our current remote data, we cannot yet rule any of them out. The origin of Vanth remains one of the most debated and fundamental questions about this system, and its answer will not only tell us how this particular moon came to be, but will also provide crucial insights into the dynamic processes that shaped all the worlds at the very edge of our sun's influence. And now we arrive at a phenomenon that seems to defy the very nature of this frozen realm, the possibility of seasons on a world without seasons. Our 11th great mystery examines the tantalizing evidence that the surface of Orcus is not a static, frozen museum exhibit, but a surprisingly dynamic landscape undergoing change. At its immense distance, the concept of seasons as we know them is almost meaningless. The sun provides negligible warmth, and the variation in solar energy between its closest and farthest points in orbit is trivial. We would expect a place like this to be locked in a perpetual, deep freeze stasis, its appearance unchanged for millennia. Yet, careful observations over time suggest something far more interesting is afoot, with the reflectivity and color of certain regions appearing to shift in ways that hint at active processes reshaping the dwarf planet's face. The most likely explanation for this activity is a slow cycle of sublimation and condensation, a kind of weather in ultra-slow motion. Even in the profound cold, the most volatile ices on its surface, like frozen nitrogen or methane, possess a minute but measurable vapor pressure. When a particular hemisphere tilts ever so slightly toward the distant sun during its long orbital journey, these ultra-thin ices might absorb just enough energy to transition directly from a solid to a gas in a process called sublimation. This escaping gas would carry away darker dust and Tholen particles, potentially leaving behind a temporarily brighter and cleaner patch of underlying water ice. Later, as that hemisphere tilts away, the temperature drops that tiny fraction of a degree further, causing the gaseous molecules to recondense back onto the surface as a new layer of frost, perhaps darkening the area once again. This incredibly subtle atmospheric breathing could be enough to cause the observed albedo variations, painting and repainting the surface in a cycle that lasts for centuries. A more dramatic driver of change could be the cryovolcanic activity we've previously suspected. If Orcus does harbor internal heat from radioactive decay or past tidal interactions, that energy might occasionally find a weak point in the icy crust and erupt outward. A plume of relatively warm water ice, laced with ammonia or salts that act as antifreeze, could spread across the terrain, flash freezing into a brilliant new plane that drastically alters the reflectivity of a vast region. This wouldn't be a seasonal change driven by the sun, but an internal, geological one, a burp from the dwarf planet's hidden interior. The resulting bright spot would then slowly darken over thousands of years as relentless cosmic radiation processed the fresh ice into darker tholins, creating a long-term, observable color cycle entirely disconnected from solar input. The extreme axial tilt of Orcus could be magnifying these effects in bizarre ways. With its poles potentially pointing almost along its orbital plane, it might experience periods where one pole receives continuous sunlight for a long portion of its 245-year orbit, while the other is in endless darkness. This could create a permanent summer and winter hemisphere on a colossal timescale, driving sustained sublimation from one pole and deposition at the other. This would not be a quick change, but over decades of observation, we might just be catching the beginning of a centuries-long trend where one half of the world gradually brightens while the other slowly darkens, a climatic wave moving in extreme slow motion. The true wonder of this mystery is that it forces us to abandon the idea of the outer solar system as a timeless, unchanging place. Orcus is teaching us that activity and geology do not require a nearby star. They can be powered by internal forces, subtle chemistry, and the gentle, persistent nudge of gravity itself. The changes on its surface are a silent testament to a slow, cold, but very much alive form of planetary evolution, proving that even in the deepest freeze, the story of a world is still being written. This brings us to a profound contradiction that lies at the heart of understanding this distant world. After all the talk of potential atmospheric cycles and cryovolcanic outgassing, our 12th great mystery is a baffling absence. Why does Orcus show no clearly detectable atmosphere? Based on everything else we suspect about it, the logical conclusion would be that it must hold onto at least a wispy, temporary envelope of gases. It has volatile ices on its surface, potential internal heat, and a large enough size to exert a meaningful gravitational pull. Yet, when we search for the telltale signs of an atmosphere, the way it bends starlight during an occultation or the specific spectroscopic signatures of gases, the results come back stubbornly negative. It's as if we're looking at a world that has all the ingredients to breathe but is somehow holding its breath indefinitely. The most straightforward explanation is that any atmosphere it does manage to generate is simply too transient and tenuous for our current instruments to detect. The gravity on Orcus is weak, only a fraction of what we feel on Earth. For a gas molecule to achieve escape velocity and fly off into space requires far less energy here than on a larger planet. This creates a scenario where the atmosphere might be in a constant state of creation and immediate destruction. The moment a patch of methane or nitrogen ice sublimates into gas, the molecules could be racing away into the void almost instantly, especially if they are warmed even slightly by the distant sun. The atmosphere wouldn't be a stable blanket, but more like a continuous, invisible geyser of particles leaping from the surface and never returning, a process known as Jean's escape. Our telescopes, taking long exposure measurements from billions of miles away, would be hard-pressed to capture such a fleeting phenomenon. Another compelling possibility involves the unique nature of its surface chemistry. The dark, tholin-rich material we suspect covers large areas might not be just a passive coating. It could be actively sealing the surface. This complex, tar-like sludge could form a porous, spongy crust that acts like a lid on a pot, trapping volatile ices beneath it and preventing them from turning to gas in the first place. Any gas that does manage to form underneath might struggle to percolate up through this thick, non-porous layer. Instead of escaping, the gases could be reabsorbed into the icy regolith or refrozen onto cold, shaded parts of the surface in a process called cold trapping. The atmosphere isn't escaping, it's being locked down, imprisoned by its own chemistry in a perpetual frozen state. We must also consider the role of temperature. Orcus's orbit is highly elliptical, meaning its distance from the Sun varies significantly over its 245-year journey. At its closest approach, it might receive just enough solar energy to trigger widespread sublimation, potentially puffing up a temporary, detectable atmosphere for a few decades. But for the vast majority of its long orbit, it is simply too far away and too cold for any significant atmospheric activity to occur. Our observations have likely captured it during this long, dormant winter phase. We may simply have not been looking at the right time, missing its brief season of exhalation by a matter of decades. Future astronomers, patiently watching over the next century, might be rewarded with the sudden appearance of a hazy envelope as Orcus swings closer to the Sun, revealing that its missing atmosphere was merely a question of celestial timing. This puzzle reminds us that our snapshots of these distant worlds are just single frames in a movie that unfolds over centuries, and the full story of Orcus's dynamic nature is still waiting to be seen. All this brings us to a mystery that exists not in the realm of physical attributes, but in the very light Orcus reflects back to us. Our 13th great puzzle lies in the world of spectroscopy, the science of breaking down light into its constituent colors to reveal the chemical fingerprints of distant objects. When astronomers train their most powerful spectrometers on Orcus, they receive data that is both a treasure trove of information and a source of profound confusion. The spectral signature of this dwarf planet contains distinct absorption features and emission bands that simply do not match the profiles of any other major trans-Neptunian object we have studied. It possesses a unique spectral personality, a combination of features that suggests either an utterly unique cocktail of surface materials or processes at work that we have not yet witnessed elsewhere in the solar system. The most immediate challenge is in identifying the exact compounds responsible for these anomalous features. We can clearly see the strong signature of crystalline water ice, which we've discussed, but superimposed upon that are other, weaker absorption bands at specific wavelengths of infrared and visible light. These bands are the telltale signs of particular chemical bonds vibrating the way molecules announce their presence across the void. The problem is, these announcements are in a language we don't fully understand. The bands don't cleanly align with the known spectra of common ices like methane, nitrogen, or carbon monoxide, nor do they perfectly match the complex profiles of the tholins we see on Pluto or Triton. It's as if we're listening to a familiar song played on unfamiliar instruments, creating a melody that is both recognizable and strangely foreign. This has led to a fascinating scientific detective hunt, with researchers proposing a host of exotic candidates to explain the data, from various ammonia hydrates and chloride salts to more complex organic molecules like cyanide compounds or acetylene. Each possibility paints a different picture of the world's formation and history. One compelling theory is that we are seeing the effects of a unique radiation environment. The surface of Orcus is bombarded by cosmic rays and solar wind particles, a relentless rain of high-energy radiation that constantly knocks atoms around and breaks molecular bonds, a process known as radiolysis. Perhaps the specific mix of ices on Orcus, when subjected to this bombardment over billions of years, has produced a novel type of radiation-processed material unlike anything created in our laboratories or observed on other worlds. The potential presence of internal heat could further complicate this picture, providing just enough energy to anneal the radiation damage in some areas and create entirely new, stable compounds that wouldn't form in a purely cold, passive environment. It's a cosmic chemistry experiment running on a planetary scale, with a recipe we are still trying to decipher. A more unsettling, though less likely, possibility is that we are being fooled by our own instruments. Spectroscopy at this distance is an exercise in extreme precision, teasing out incredibly faint signals from an overwhelmingly noisy background. The anomalous features could be artifacts introduced by the Earth's atmosphere, which itself absorbs certain wavelengths of light, or by subtle calibration issues within the telescopes and spectrometers themselves. Ruling out this mundane explanation requires repeated observations from different instruments at different times, a painstaking process that is still ongoing. However, the fact that these peculiar features persist across multiple independent observations makes it increasingly probable that the anomaly is real, a genuine feature of Orcus that distinguishes it from its icy cousins. Ultimately, these spectral signature anomalies are more than just a chemical puzzle. They are a direct challenge to our classification systems. We tend to group Kuiper Belt objects into broad categories: the Pluto-like objects, the Haumea-like objects, the Makemake-like objects. Orcus refuses to fit neatly into any of these boxes. Its unique light signature suggests it may be the prototype of a new, rare class of world, one that formed under special conditions or has undergone a unique evolutionary path. Unlocking the secret of its spectrum is therefore crucial. It doesn't just tell us what Orcus is made of, it forces us to expand our entire understanding of the chemical diversity possible in the outer solar system, hinting at a richness and complexity in the frozen fringe that we are only beginning to appreciate. The path of Orcus through the solar system holds yet another layer of intrigue, one that moves beyond its resonant rhythm with Neptune to consider the very angle of its orbit. This 14th mystery delves into the peculiarities of its orbital inclination, the measure of how steeply its path is tilted relative to the relatively flat plane where most planets orbit. While many Kuiper Belt objects have significant inclinations, that of Orcus is particularly pronounced and appears to be precisely maintained, a characteristic that sets it apart from other objects locked in the same 2 to 3 resonance with Neptune and raises compelling questions about the forces that sculpted its journey. Most planets and large asteroids orbit within a few degrees of the ecliptic plane, the dusty disk left over from the Sun's formation. This makes intuitive sense as they all coalesced from that same spinning, flattening cloud of gas and dust. The classical Kuiper Belt, home to many well-known objects, also largely occupies this region. Orcus, however, bucks this trend with an orbital inclination of roughly 20 degrees. This is a substantial tilt, meaning its path carries it far above and below the main orbital plane for a significant portion of its long journey around the Sun. This in itself is not entirely unusual. Gravitational interactions during the solar system's chaotic youth famously scattered many objects into such tilted and eccentric orbits. The real puzzle is not that its orbit is inclined, but that this specific inclination is so stable and appears to be a fundamental, unchanging feature of its identity. This stability is the heart of the mystery. In the dynamic gravitational environment of the outer solar system, the orbits of smaller bodies are typically subject to gradual perturbations. The constant, subtle tugs from the giant planets, especially Neptune, should over time alter the inclination of an object like Orcus, either increasing it or circularizing it closer to the mean plane. The fact that Orcus has maintained its distinctive 20-degree tilt for billions of years suggests that its orbital parameters are not random or decaying, but are instead locked in, almost as if they are being actively preserved by some unseen mechanism. It possesses a gravitational signature of remarkable resilience. So what could have imparted this specific tilt and then safeguarded it across eons? The most widely accepted theory points to the great planetary migration that is believed to have occurred in our solar system's infancy. According to the NICE model, the giant planets Jupiter, Saturn, Uranus, and Neptune formed much closer together before gravitational instabilities caused them to migrate outward, scattering icy planetesimals throughout the system in the process. It's conceivable that during this tumultuous period, a close gravitational encounter with one of these migrating giants, most likely Neptune, could have given Orcus a powerful gravitational kick, launching it into its current inclined and resonant orbit. The same event that established its 2 to 3 rhythm with Neptune may have also set its orbital tilt, a 1-2 punch from a planetary billiard ball that defined its path forever. However, this explanation, while compelling, may not be the full story. The pristine maintenance of its inclination hints that something else might be at work, perhaps a continuing gravitational influence that acts as a stabilizing hand. This is where more speculative and thrilling ideas enter the picture. Some dynamicists have proposed that the combined gravity of the other innumerable Kuiper Belt objects, what's known as the self-gravity of the belt, could create a faint background potential that helps shepherd and maintain the orbits of larger bodies like Orcus, preventing their inclinations from drifting over time. The most dramatic hypothesis, though, involves the potential influence of a much larger, undiscovered body, the theorized Planet 9. This hypothetical planet, predicted to be several times the mass of Earth and orbiting far beyond Pluto, would exert a powerful gravitational influence on the entire outer solar system. Its presence is invoked to explain the unusual clustered orbits of several extreme trans-Neptunian objects. It is entirely plausible that the same distant gravitational shepherd that groups those objects together is also subtly constraining the orbit of Orcus, helping to maintain its specific inclination against the perturbing forces of the known planets. In this scenario, the tilted path of Orcus becomes not just a relic of a past encounter, but an ongoing dialogue with a hidden giant, a clue written in its motion that points toward one of astronomy's greatest potential discoveries. Ultimately, the orbital inclination of Orcus is far more than a simple celestial statistic. It is a preserved record of the most violent and formative era of our solar system, a fossilized trajectory that captures the moment of its own gravitational scattering. Its stubborn persistence challenges the completeness of our models and invites us to consider the possibility of unseen actors still shaping the dance of the worlds from the shadows. By studying the precise angle of its path, we are reading a history of chaos and order, a story where a world was kicked into the darkness, only to find a perfectly balanced and enduring groove in the void. Yet another layer is added to the puzzle when we consider the very mass of Orcus in relation to its volume, a fundamental property that leads us straight into our 15th great mystery, the confounding density conundrum. Density is a deceptively simple number calculated by dividing an object's mass by its volume, yet for a distant world, it is one of the most difficult and revealing measurements to pin down. It tells us the ratio of rock to ice, of solid material to empty space, and ultimately, the very structural integrity of the world. For Orcus, this number has become a source of intense debate, as the conflicting estimates of its size and mass yield two wildly different portraits of its internal nature, forcing us to question whether it is a solid, rocky body or a porous, icy shell potentially hiding vast caverns or even a global ocean within. If we take the measurements that suggest a smaller diameter and thus a smaller volume, the calculated density for Orcus becomes surprisingly high. A high density implies a world that is predominantly rock, with only a relatively thin mantle of water ice and other volatile compounds on its surface. This would be a fascinating revelation, as it would suggest Orcus formed much closer to the Sun, in the warmer region of the primordial solar nebula near the forming gas giants. In this hotter environment, the intense light from the young Sun would have blown away the lighter, icy materials, allowing mostly rocky dust to accrete into a dense core. This rocky protoplanet would then have been gravitationally scattered outward during the Great Planetary Migration, finding its current home in the Kuiper Belt billions of years ago. A dense, rocky Orcus would also make the origin of its large moon Vanth even more perplexing, as a giant impact on a rocky body would require even more catastrophic force to eject enough material to form a companion of that size. Conversely, if the larger size estimates are correct, the math points to a dramatically lower density. A low-density Orcus would be an icy world through and through, a body more akin to a compacted snowball than a rocky planetesimal. Its structure would likely be highly porous, filled with voids and caverns between icy grains that never fully compressed under its own weak gravity. This would paint a picture of a world that formed in situ, right where it resides today in the cold outer solar system, accumulating directly from the icy planetesimals that populated the region. It would be a pristine, primordial relic, largely unchanged since the dawn of the solar system. This interpretation would make the presence of crystalline water ice on its surface more puzzling, as a porous, fluffy body would struggle to retain the internal heat needed to process amorphous ice into its crystalline form, and would be unlikely to support any kind of subsurface ocean. This discrepancy is not merely a matter of academic preference, it forces us into a fundamental choice between two completely different origin stories. Is Orcus an immigrant from the inner solar system, a rocky interloper that was ejected into the icy depths? Or is it a native of the outer solar system, a classic icy body that has always resided in the frozen fringe? Our entire understanding of its history, its geology, and its relationship with its moon hinges on this single number. The frustrating truth is that our current remote observations cannot yet tell us which value is correct. The uncertainty in its size, perhaps due to an unusually fluffy and ill-defined surface layer or an oblong shape, propagates directly into this critical calculation of density. The most thrilling possibility, however, is that the truth lies somewhere in the middle, and that the density conundrum itself is the clue pointing toward an even more fascinating internal structure. Perhaps Orcus does have a dense, rocky core, but it is surrounded by a thick mantle of ice that is not solid, but instead contains massive subsurface voids or a global porous layer. Alternatively, the same potential internal heat that might power cryovolcanism could be maintaining a layer of liquid water or a slushy ocean deep beneath the crust, effectively lowering the average density of the entire world. A deep, liquid water ocean would have a density lower than rock but higher than ice, which could help reconcile the conflicting measurements. The density of Orcus may not be a simple number at all, but an average of drastically different layers: a rocky heart, a watery mantle, and an icy, porous crust, creating a complex, differentiated world that defies our simple binary categories of either rocky or icy. Until we can send a probe to measure its gravitational field directly, the true density of Orcus will remain one of its most guarded secrets, a numerical paradox that holds the key to unlocking the entire story of what this distant world is truly made of. This brings us to a subtle yet deeply significant puzzle, not of Orcus itself, but of its silent partner, Vanth. Our 16th mystery delves into the curious rotational state of this moon, a characteristic that on the surface seems perfectly normal but upon closer inspection reveals a profound inconsistency. Vanth appears to be in synchronous rotation with Orcus, meaning it always shows the same face to its parent world, much like our moon does with Earth. This tidal locking is a common and expected outcome in planetary systems. Given enough time, gravitational interactions between a planet and its moon will slow the moon's rotation until it becomes synchronized with its orbital period. The mystery here is not that it's locked, but the unsettling implication that, according to our best theoretical models, it really shouldn't be locked yet. For a system of this size and at this distance, the process of tidal locking should take far longer than the current age of the solar system. The mechanism behind tidal locking is a gentle but persistent gravitational tug of war. The gravity of the larger body, Orcus in this case, exerts a slightly stronger pull on the nearer side of the moon than on its far side. This differential pull creates a slight bulging effect on the moon, and as the moon rotates, this bulge is constantly being pulled out of alignment. This friction, this constant effort to realign the bulge, acts as a brake, slowly sapping the moon's rotational energy over billions of years until its spin perfectly matches its orbit. The time it takes for this process to complete depends on several factors: the mass of the primary body, the distance between the two objects, and the initial rotational energy of the moon. For large moons orbiting close to massive planets, like the Galilean moons of Jupiter, this can happen relatively quickly on a cosmic timescale. But for a small, distant system like Orcus and Vanth, the gravitational forces at play are incredibly weak. Our models suggest that the tidal forces between these two bodies are so feeble that the process of synchronization should require tens of billions, perhaps even hundreds of billions of years, a time frame that stretches far beyond the 4.5 billion years our solar system has existed. This leaves us with a glaring chronological paradox. We are observing a finished process, a moon that has already reached its final, locked state, in a system that our physics says is far too young for such an event to have occurred. It's as if we walked into a room to find a candle that had completely burned down, but the match used to light it was still striking. The synchronization is an accomplished fact, but the means to achieve it within the allotted time seem to be missing. This forces us to re-examine our assumptions and consider what we might have wrong about this distant pair. One compelling possibility is that our models for tidal locking in the Kuiper Belt are simply incomplete. The equations we use were developed for stronger gravitational fields and different material compositions. Perhaps the ices that make up these bodies are far more dissipative than we've assumed, meaning they generate much more internal frictional heat from the flexing caused by tidal forces. If the interiors of Orcus and Vanth are mushier, slushier, or more viscous than our models account for, this internal friction would have acted as a much more effective brake, sapping Vanth's rotational energy at a dramatically accelerated rate and allowing it to become locked within the solar system's lifetime. The potential presence of a subsurface ocean on either body, which would create a much more fluid and responsive layer to gravitational tugging, could also have drastically shortened the locking timescale. Another fascinating theory involves a much more violent and rapid path to locking. Perhaps Vanth did not achieve its synchronous rotation through the slow, gentle process of tidal braking. Instead, it may have been born locked. If the Moon formed directly from a debris ring created by a giant impact on Orcus, the material in that ring would have naturally coalesced very close to the dwarf planet, well inside what's known as the synchronous orbit radius. At that close distance, the orbital period would have been very short, and the new Moon would have essentially formed already tidally locked, its rotation inherent to its birth from the very beginning. It would have then migrated outward to its current position over time, all the while maintaining its locked state. This would neatly solve the timing problem, making the slow process of tidal braking unnecessary. The gravitational interactions between Orcus and Vanth that allowed this outward migration could themselves have helped reinforce the lock. The synchronous rotation of Vanth is a quiet, almost hidden mystery, but its implications are enormous. It suggests that either our fundamental understanding of tidal physics in the outer solar system is flawed, or that the history of this system was far more dynamic and dramatic than its current serene appearance would suggest. This isn't just a question about a moon's spin. It's a test of our physical models applied to the most distant and alien environments in our solar system. Getting this right is crucial because if we misunderstand the basic forces at work here, it changes how we interpret the geology, thermal history, and potential for activity on countless other icy worlds in the Kuiper Belt and beyond. The silent, locked gaze of Vanth towards Orcus is a challenge, a call to refine our physics and to understand the subtle yet powerful forces that shape worlds in the deep freeze of space. Now we turn our gaze from the dynamic forces shaping Orcus to the very fabric of its surface, where a new enigma is written in the language of craters and plains. Our 17th Great Mystery confronts a stark contradiction that has left planetary geologists utterly perplexed. The surface of Orcus appears to be two different ages at once. High-resolution images, though limited to a handful of pixels, reveal a world seemingly caught between two eras. Vast regions are heavily cratered, bearing the pockmarked scars of a surface that has remained unchanged for billions of years, a fossilized record of the violent bombardment that characterized the early solar system. This is precisely what we expect to find in the frozen, inert depths of the Kuiper Belt. Yet, right alongside these ancient landscapes are astonishingly smooth, flat expanses that show a near-total absence of impact craters. These plains are so pristine they appear to have been wiped clean, geologically speaking, in the relatively recent past. This is a profound paradox. A surface cannot be both 4 billion years old and a few 100 million years old simultaneously. One of these observations must be deceiving us, or we are witnessing a form of geological activity that fundamentally challenges our understanding of how these distant, cold worlds operate. The presence of ancient cratered terrain is the default expectation. The rate of impacts in the Kuiper Belt, while not zero, is incredibly low today. Once a surface becomes cratered, it should remain that way, its appearance frozen in time like a photograph of the solar system's violent youth. The heavily cratered areas on Orcus are its history books, their dense collection of impact sites testifying to an era when space was far more crowded with debris. The sheer number of craters in these regions suggests they have been exposed and untouched since not long after the dwarf planet itself formed, making them some of the most ancient landscapes we can observe in our cosmic neighborhood. They represent the Orcus we expected to find, a static, unchanging relic. The existence of the young, smooth plains, however, shatters that simple picture. A lack of craters means a lack of impacts, which in turn means the surface hasn't been there long enough to be hit. In geological terms, these plains are newborn. For them to exist, something must have actively erased the previous cratered terrain and laid down a brand new surface layer in the relatively recent past. This process is called resurfacing, and it requires a significant source of energy and geological activity. On a warm, rocky world like Earth, we have plate tectonics and volcanism to refresh the surface. On a geologically active icy moon like Europa, the constant churning of a subsurface ocean cracks and renews its icy crust. But on a small, cold, remote dwarf planet like Orcus, located in the deep freeze of the solar system, all the conventional sources of energy for such renewal have been presumed absent for eons. There is no internal heat from radioactive decay, no significant tidal heating from gravitational interactions, and certainly no energy from the faint, distant sun. The existence of these smooth plains is therefore a declaration that our assumptions are wrong. Orcus must possess an engine for change that we have not yet identified. So what could be powering this mysterious resurfacing? The most compelling candidate remains cryovolcanism. Imagine not a volcano of fire and rock, but one of ice and slush. If Orcus retains enough internal heat, perhaps from the decay of long-lived radioactive elements, or from the residual warmth of its formation, or from past tidal interactions, it could maintain a subsurface ocean or pockets of liquid water mixed with ammonia or salts that act as a powerful antifreeze. Occasionally, the pressure from this buried liquid could overcome the strength of the overlying icy crust, causing a rupture. This would not be a violent, explosive eruption, but a slow, viscous oozing of a thick, slushy mixture onto the surface. This cryolava would flow across the ancient, cratered terrain, filling in the depressions and creating a vast, smooth, new plain that would then flash freeze in the vacuum of space. This process would effectively hit the reset button on that region's geological clock, creating the unnervingly young surfaces we infer from the absence of craters. Another possibility involves the slow, global process of sublimation and condensation, a form of icy weathering on a planetary scale. Over millions of years, the most volatile ices on the surface, like frozen methane or nitrogen, could be slowly sublimating away from warmer areas and redepositing as frost in colder, shaded regions. This incredibly gradual migration of material could slowly blanket and soften the topography, filling in smaller craters and creating the illusion of smoother plains. However, this process is likely too slow and gentle to account for the complete eradication of large impact craters that a truly smooth plain would require. It might modify a landscape but not completely renew it. The most dramatic resurfacing agent of all could be a massive impact, but from a different perspective. While an impact typically creates a crater, a truly colossal collision could have the opposite effect. A gargantuan impact event, one that nearly shattered Orcus, could have generated so much heat that it triggered global melting of the icy crust. The entire surface could have literally turned into a temporary, global slushy ocean before slowly refreezing into a brand new, smooth crust. This would have erased all previous geological history in one catastrophic event. While this would explain the clean slate, it would have been an event of such violence that it's difficult to reconcile with the survival of Orcus as a single body and the continued existence of its moon Vanth in a stable orbit. The surface age discrepancy is more than a geological curiosity. It is a direct challenge to our classification of these distant worlds as dead and inert. Orcus is forcing us to accept that geological activity is not solely the domain of planets with strong internal heat or moons under intense gravitational stress. It suggests that even in the deepest, coldest reaches of our solar system, worlds can harbor their own slow, cold, but very real geological hearts, beating over billion-year timescales to occasionally remake their own faces. This mystery transforms our view of the Kuiper Belt from a silent graveyard of frozen fossils into a place where the slow, patient drama of planetary evolution is still quietly unfolding. This glaring contradiction between its location and its luminosity forms our 18th great mystery, the albedo paradox of Orcus. In the profound darkness of the Kuiper Belt, most objects are dim and somber, their surfaces darkened over billions of years by an unceasing rain of cosmic radiation that cooks simple ices into a dark, reddish-brown sludge known as tholins. We expect these distant worlds to be among the least reflective places in the solar system, cosmic charcoal briquettes fading into the void. Orcus, however, defiantly breaks this mold. It shines with a significantly higher albedo, meaning it reflects a much larger portion of the feeble sunlight that reaches it, making it appear surprisingly bright against the blackness of space. This superior reflectivity is a clear signal that its surface is not the ancient, radiation-blasted landscape we anticipated, but something far more dynamic and unusual. The most immediate and thrilling explanation for this abnormal brightness is the persistent presence of fresh, clean ice. As we've explored with the crystalline water ice and the mysterious bright spot, the surface of Orcus appears to be subject to ongoing renewal processes that are actively covering up the dark, aged material. This is the heart of the albedo paradox. Its high reflectivity isn't a static property, but a dynamic state of being. It suggests an active world, one that is constantly repainting its own surface. The primary artist in this renewal is almost certainly cryovolcanism. If plumes of water ice mixed with ammonia are periodically erupting from its interior, they would spread across the terrain like a geological whitewash, covering the old, dark tholins with a brilliant new layer of pristine, highly reflective frost. Each eruption would reset the albedo clock for that region, creating a temporary beacon of light that slowly dims over millennia as radiation processes the new ice back into dark compounds. The paradox is not that it's bright, but that the brightness is being maintained against the relentless darkening forces of the space environment. Beyond explosive events, more gentle processes could also be contributing to this high reflectivity. The potential for a slow, sublimation-driven weather cycle could be continually cleansing the surface. As the most volatile ices turn to gas and escape, they could be carrying away embedded dark dust and radiation-reddened particles with them, effectively sandblasting the surface with escaping gas and leaving behind a cleaner, brighter layer of water ice. This would be a less dramatic but more continuous form of renewal, a constant exhalation that keeps the world looking younger than its years. Furthermore, the specific composition of the ice itself might be a factor. The potential presence of ammonia hydrates or certain salts within the ice could change its physical structure at a microscopic level, causing it to form smaller, more numerous crystals that scatter light far more efficiently than large, grainy ice crystals would. This would be akin to the difference between a sheet of smooth glass and a pile of crushed glass or snow. The latter is vastly brighter because it has more surfaces to reflect light. Orcus's ice might be inherently engineered for maximum reflectivity due to its unique chemical recipe. This albedo paradox forces a complete re-evaluation of what geologic activity means in the outer solar system. We can no longer assume that distance from the Sun equates to geologic death. Orcus is demonstrating that internal heat, whether from radioactive decay, tidal interactions, or the remnant energy of its formation, can persist for billions of years in even modestly sized bodies, fueling processes that keep their surfaces young and bright. Its high reflectivity is therefore not a simple observation, but a proxy measurement for its hidden vitality. It is a world fighting back against the entropic decay of space, actively maintaining its brilliant complexion in the endless cosmic night, a silent testament to the fact that even in the deepest freeze, planetary life finds a way. The journey of Orcus to its present celestial address is a cold case buried deep in the solar system's history, a mystery that asks not just where it is, but how it got there. This 19th enigma confronts the fundamental question of its origin. Is this dwarf planet a true native of the Kuiper Belt, a primordial piece of the outer solar system that formed right where we see it today? Or is it an immigrant, a world that began its life much closer to the Sun before being violently evicted by the gravitational turmoil of the giant planets and sent to its current frozen exile? The answer to this question of orbital migration would rewrite entire chapters of our solar system's biography, and the evidence we have for Orcus points in conflicting directions, leaving its true history shrouded in uncertainty. If Orcus is a true native, it would have coalesced directly from the icy planetesimals that populated the primordial disk beyond Neptune. In this scenario, its composition should be a relatively pristine mix of ice and rock, largely unchanged since the solar system's birth. Its density would be low, its structure porous, and its surface would be dominated by the original, ancient materials of the cold outer disk. This origin story paints a picture of Orcus as a time capsule, a perfectly preserved relic of the conditions that existed over 4 billion years ago. Its current orbital resonance with Neptune would then be a feature it grew into naturally as the solar system settled into its current configuration, a gentle gravitational relationship established early on and maintained ever since. This is the simplest story, and for many classical Kuiper Belt objects, it is the accepted narrative. However, the peculiar characteristics of Orcus make it a terribly awkward fit for this simple native narrative. Its potential high density, suggested by some measurements, points toward a much rockier composition. Rock condenses more readily in the warmer regions of the protoplanetary disk closer to the Sun. A rocky Orcus suggests it likely formed in the neighborhood of the gas giants, perhaps between the orbits of Jupiter and Neptune, where stronger sunlight had blown away the lighter icy materials, allowing mostly rocky dust to accrete. This would make it an interloper in the Kuiper Belt, not a native. Its journey to the fringe would have been a violent one, a gravitational slingshot event during the solar system's great upheaval. This chaotic period, detailed in the leading NICE model of planetary migration, saw the giant planets shift their orbits, their immense gravity acting like a cosmic pinball machine, flinging countless smaller objects inward toward the Sun and outward into the distant darkness. Orcus, in this telling, was one of these unfortunate refugees, cast out from the warmer inner system to its current frigid abode. The plot thickens when we consider its precise orbital resonance with Neptune. A 2-to-3 resonance is a delicate relationship. For an object that was violently scattered outward, achieving such a perfectly tuned orbit is astronomically difficult. It's the difference between being thrown from a moving car and accidentally landing perfectly in a specific passenger seat of another car driving in a synchronized convoy. The odds are incredibly low. This has led to a more nuanced theory that Orcus's migration was not a single, violent event, but a slower, more graceful process known as resonant capture. As Neptune migrated outward in its early history, its gravitational influence swept through the disk of icy objects. Orcus may have been caught in the expanding wave of Neptune's gravity, like a surfer catching a wave, and gently guided into its current stable resonance. This process allows for a scattered object to find an ordered home, bridging the gap between the violent exile theory and the current observed harmony. But perhaps the most tantalizing possibility involves forces we have yet to fully chart. The specific and stable parameters of Orcus's orbit, including its inclination and eccentricity, have just the right characteristics to potentially be influenced by the hypothesized planet 9. This undiscovered giant lurking in the extreme outer solar system is theorized to shepherd the orbits of several distant objects. It's conceivable that after being scattered outward by Neptune, Orcus's path was further sculpted and stabilized by the distant gravitational tug of this unseen world, which helped lock it into its current precise relationship with Neptune and sculpted its orbital tilt. In this scenario, the migration of Orcus was a two-act drama, an initial ejection by a known giant followed by a subtle, ongoing guidance from a hidden one. Its orbit becomes a cosmic breadcrumb, a clue left behind from the solar system's chaotic youth that could lead us to one of astronomy's greatest discoveries. Unraveling the true story of how Orcus arrived at its distant post is therefore about much more than a single dwarf planet. It is a direct investigation into the most dynamic and violent era of our solar system's creation, a forensic analysis of a 4-billion-year-old journey whose evidence is written in the silent motion of a frozen world. Yet another layer of visual intrigue is added by the 20th mystery, the baffling and seemingly random color variations observed across the surface of Orcus. When astronomers map its globe, they don't see a uniform, predictable gradient of color that you might expect from a world whose only energy source is a faint, distant sun. Instead, they find a chaotic patchwork of hues. Some regions appear a brilliant, almost blinding white, while others are a deep, rusty red, with a whole spectrum of mottled grays and tans in between. The most perplexing part isn't the existence of these different colors, but their distribution and behavior. These variations don't follow any logical pattern that can be explained by simple solar heating, seasonal shifts, or even obvious geological boundaries like crater walls or plains. The dark and light patches are jumbled together in a seemingly haphazard mosaic, a cosmic abstract painting that defies our attempts to find its meaning, suggesting that unknown and highly localized processes are actively at work repainting its surface. If solar radiation were the primary artist, we would expect a much more orderly canvas. On most airless bodies, the areas that receive the most sunlight, typically the equator and sun-facing slopes, are the most heavily processed by radiation. This relentless bombardment should darken and redden those surfaces more than the poles or shaded regions, creating a predictable global pattern of color variation. Orcus completely ignores this rule. Its bright and dark spots show no apparent correlation with latitude or longitude. A brilliantly reflective patch can sit right next to a deep red one at the equator, while a polar region might show a confusing mix of both. This rules out simple, passive space weathering as the sole cause and points toward something far more active and idiosyncratic shaping the dwarf planet's appearance. Theories attempting to explain this chaotic color map are as fascinating as the puzzle itself. The leading idea involves the slow, persistent seepage of volatile materials from beneath the surface. Imagine that Orcus's crust is not a solid, impermeable shell, but a fractured lid over a complex interior. Through these cracks and fissures, highly volatile ices like methane, nitrogen, or carbon monoxide could be slowly sublimating, turning directly from a solid to a gas. As this gas escapes, it wouldn't just vanish, it would carry with it any embedded dark, dusty particles of tholin-like material, effectively scouring that specific area clean and leaving behind a temporary bright spot of fresher water ice. This wouldn't happen uniformly across the globe, but in highly localized vents and fumaroles, creating a random sprinkling of bright spots exactly as we observe. The process would then reverse as the newly exposed ice itself is slowly darkened by radiation over millennia, until another gaseous eruption nearby clears a new patch, creating an endlessly shifting, unpredictable quilt of old and new terrain. Another compelling possibility ties directly into the potential for cryovolcanic activity. If plumes of slushy water ice are indeed erupting from below, they wouldn't necessarily cover the entire surface in a uniform sheet. Each eruption would be a localized event, painting a single, specific region with a bright new coat of cryolava. The size and shape of these flows would depend on the viscosity of the erupting material and the topography it flows across, leading to the irregular, splotchy patterns of high reflectivity we detect. The older, undisturbed crust surrounding these fresh flows would remain dark from billions of years of radiation processing, creating the stark contrast between the two. This would mean the color variations are essentially a map of the most recent geological activity, with each bright spot marking the site of a relatively recent cryovolcanic event. Perhaps the most exotic theory involves the unique composition of the dark material itself. We've already noted that its spectral signature doesn't perfectly match other known tholins. It's possible that this material isn't just a passive layer of tar, but is actively changing in color based on subtle shifts in temperature or exposure to different types of radiation. Certain complex organic compounds can undergo photochemical reactions that alter their color over time. A patch of dark material might shift from red to gray or vice versa, depending on the angle of the sun or the depth at which it lies, without any change in its physical structure. This would introduce a layer of color variation that is purely chemical and not geological, a surface that changes its appearance based on a cryptic set of photochemical rules we have yet to decipher. The chaotic color variation of Orcus is a mystery that can likely only be solved from up close. It represents the culmination of all the other enigmas we've explored: the internal heat, the potential cryovolcanism, the unique chemistry, all manifesting visually on its surface. It is the clearest evidence yet that this distant world is not a static fossil, but a complex and dynamic body with its own slow, cold, and utterly alien form of life, its face constantly being remade by processes we are only beginning to imagine. Now we journey into a realm of science that can feel almost like cosmic forensics, turning from what we can see to what we can feel, or more precisely, what heat Orcus itself is giving off. This 21st mystery delves into the perplexing case of its thermal emissions, a subject where the data we receive tells a story that starkly contradicts the tale we expect from a frozen world 4 billion miles from the Sun. When astronomers point sensitive infrared telescopes toward Orcus, they are not just measuring the faint sunlight it reflects. They are measuring the tiny amount of heat it radiates back into space, a product of its own temperature. In the unimaginable cold of the Kuiper Belt, that temperature should be almost unthinkably low and, crucially, uniform. The primary heating source is solar radiation, and at that distance, its effect is so minimal that an object like Orcus should be a nearly identical ball of deep cold across its entire surface, with only the most minuscule, predictable variations. The measurements, however, reveal something entirely different. A confusing and irregular thermal map with unexpected hot and cold spots that simply cannot be explained by sunlight alone. This inconsistency presents a profound challenge to our models, forcing us to consider that Orcus is not the passive, frozen relic we imagined, but a world with its own hidden sources of energy or incredibly unusual physical properties. The immediate and most thrilling explanation for these thermal irregularities is the presence of some form of internal heat. For a small, rocky, icy body billions of years old, this seems counterintuitive. The heat from its initial formation should have dissipated eons ago, and it is generally considered too small to host significant long-lived radioactive elements like potassium-40 or thorium-232 that keep Earth's interior hot. Yet, other mechanisms could be providing a steady, internal energy source, tidal heating generated by the gravitational pull of its large moon Vanth could be a prime candidate. If their orbit has ever been, or still is, even slightly elliptical, the constant flexing and relaxing of Orcus's interior caused by Vanth's varying gravitational pull would generate friction and consequently heat. This is the same process that powers the spectacular cryovolcanism on Jupiter's moon Europa. Even a small amount of residual tidal heating could be enough to create localized warm spots where this energy seeps to the surface through cracks and fissures, potentially even sustaining a subsurface ocean and further fueling the possibility of the cryovolcanic activity we see evidence for elsewhere. Another compelling possibility involves a transient, ultra-thin atmosphere engaged in a slow-motion cycle of creation and destruction. On worlds like Pluto, the slow sublimation of surface ices where solid turns directly to gas can create a temporary atmosphere that acts as a vehicle for redistributing heat. Perhaps on Orcus, pockets of highly volatile ices like methane or nitrogen are warming in the fleeting sunlight, turning to gas. This process of sublimation actually absorbs heat from the immediate environment, creating a localized cold spot. That gas might then travel across the dwarf planet before collapsing back onto the surface as frost in a colder region, a process called condensation that releases latent heat and warms that area. This atmospheric puffing would act like a planetary breath, continuously reshuffling the thermal deck and creating a patchwork of temperatures that completely defies a simple model based on solar exposure alone. However, directly detecting such a wispy, intermittent atmosphere with our current technology is nearly impossible from Earth, leaving it a tantalizing but unproven hypothesis. We must also consider that the bizarre thermal map might be a direct and passive consequence of the strange mix of materials on its surface, a property known as thermal inertia. Different substances absorb, store, and radiate heat at vastly different rates. A patch of dark, reddish tholin-rich terrain would act like a black car on a summer day, absorbing more of the feeble sunlight than a neighboring area of brilliant white water ice, which would act like a white car, reflecting most of the solar energy away. This could create a situation where a dark patch becomes slightly but measurably warmer than its bright surroundings, even though both are receiving the exact same amount of energy from the distant sun. The scale and intensity of the temperature differences observed on Orcus, however, suggest that composition alone is not the full story. It appears that an active process is continually refreshing this thermal landscape, preventing it from settling into the dull, uniform equilibrium we would expect from a dead world. Of course, we must always entertain the possibility that the anomaly is not with Orcus, but with our own observations. Measuring the thermal emissions of a pixel-sized object at the edge of the solar system is one of the most difficult tasks in modern astronomy. The signals are incredibly faint and must travel through our own planet's turbulent atmosphere, which itself absorbs and emits infrared radiation, adding noise to the already weak data. There is a chance that what we interpret as hot and cold spots on Orcus are actually artifacts introduced by atmospheric interference or instrumental error. Perhaps our models for how to interpret the raw infrared data are incomplete for an object with such a unique surface composition. Ruling out these mundane explanations requires repeated observations from different telescopes at different times, a painstaking process that continues to this day. Yet, the persistent nature of these thermal anomalies across multiple studies makes it increasingly likely that we are seeing a real phenomenon, a genuine mystery of heat and cold playing out on the surface of this distant dwarf planet. Ultimately, these thermal emission anomalies paint a picture of a world that is far more complex than a simple ball of ice and rock. They are the invisible signature of Orcus's hidden vitality, deeply interconnected with all the other mysteries we've explored. The same internal heat that could explain the warm spots might also power the cryovolcanism that creates the bright, reflective plains and keeps the water ice in a crystalline state. It suggests a delicate and ongoing ballet of energy where internal forces, atmospheric whispers, and complex surface chemistry interact to create a thermal environment that is unique in the outer solar system. This isn't just a scientific discrepancy, it's a clue that Orcus has its own hidden energy budget and a slow, cold geological heartbeat, operating on a cosmic timescale in the profound silence of the solar system's deepest frontier. Now we come to a mystery that challenges our most fundamental understanding of gravitational relationships in the outer solar system, a puzzle that pits the clockwork precision of celestial mechanics against the immense, patient stretch of cosmic time. Despite having spent over 4 billion years circling one another in their slow, distant dance, the Orcus-Vanth system shows no sign of having achieved a state of full, mutual tidal locking. This is a profound anomaly. Tidal locking is one of the most predictable and inevitable processes in orbital mechanics. Given enough time, the gravitational interaction between two bodies will inevitably slow their rotations until they forever present the same face to one another, just as our moon does with Earth. For a system as old as Orcus and Vanth, we should be looking at a perfectly synchronized pair, a finished product of gravitational friction. The fact that we are not forces us to question whether our models of tidal physics are incomplete, or if unseen forces are actively preventing this system from settling into its expected final state. The mechanics of tidal locking are deceptively simple in theory but immensely complex in their details. The gravitational pull of the larger body, Orcus, creates a slight bulge on the smaller moon, Vanth. As Vanth rotates, this bulge is constantly tugged out of alignment, and the energy lost in this constant flexing acts as a brake, slowly sapping the moon's rotational momentum. For most planet-moon systems, this process concludes within a few billion years. The fact that it hasn't for Orcus and Vanth suggests the braking mechanism is far less effective than our models predict. The most likely culprit is the sheer distance between them. Vanth orbits Orcus at a significantly wider berth than many other comparable moon systems. Tidal force decreases with the cube of distance, meaning that even a small increase in separation results in a dramatic drop in gravitational influence. The weak tug from Orcus is simply too feeble to have effectively slowed Vanth's spin within the age of the solar system, leaving the moon with some residual rotation. However, distance alone may not tell the whole story. The internal structure of these bodies plays a critical role in how they respond to tidal forces. Our standard models often assume fairly homogeneous, solid interiors, but if either Orcus or Vanth has a particularly rigid, solid core surrounded by a less viscous mantle, it would be far less susceptible to the flexing that generates tidal friction. A world that doesn't flex doesn't break. Conversely, if one of them possesses a subsurface global ocean, a layer of liquid water between a solid core and an icy shell, this would change the equation entirely. A liquid layer effectively decouples the shell from the core, allowing the crust to rotate more freely and independently, dramatically reducing the tidal forces that would otherwise slow its spin. The presence of such an ocean could act as a lubricant, preventing the system from ever achieving full lockdown and preserving its primordial rotation. We must also consider the possibility that their orbital resonance with Neptune is indirectly influencing this process. Orcus is locked in a precise 2 to 3 resonance with the ice giant, meaning its own orbit is periodically tweaked by Neptune's gravity. These regular gravitational nudges, however subtle, could be providing just enough energy to the Orcus-Vanth system to counteract the weak tidal braking. It's as if Neptune is giving the system a tiny, periodic kick, preventing it from ever fully settling down. The entire binary pair might be trapped in a meta-stable state, their rotation and orbit delicately balanced by these external influences, forever on the verge of locking without ever quite achieving it. Furthermore, the possibility that Vanth itself was a captured object rather than a co-formed moon adds another layer of complexity. a captured moon would have entered the system with a much higher initial rotational energy and orbital eccentricity. It would take far longer for tidal forces to circularize its orbit and slow its spin from such a wild starting point. If the capture was a relatively recent event on a cosmic timescale occurring only 1 billion or 2 years ago rather than at the dawn of the solar system, then it would easily explain why the system hasn't had sufficient time to reach a locked equilibrium. The implications of this failed lockdown extend far beyond this single pair. If our understanding of tidal physics is genuinely flawed for these distant, icy systems, it means we may be misinterpreting the geological potential of countless other Kuiper Belt objects and moons across the solar system. A moon that isn't tidally locked might not experience the internal heating that drives cryovolcanism, or it could have a completely different thermal and geological history than our models predict. The unresolved tidal relationship between Orcus and Vanth is therefore a quiet but monumental challenge to astrophysics, a subtle hint that in the deep freeze of the outer solar system, the rules of celestial engagement may be written in a language we are only beginning to translate. Even as we map its craters and plains with increasing clarity, a more terrestrial mystery surrounds this distant world, the curious and protracted delay in formally naming any of its surface features. While we have detailed maps of Pluto's heart-shaped Tombaugh Regio and the dark Cthulhu Macula, and while even smaller asteroids have craters and ridges bearing official names, the fascinating landmarks of Orcus remain anonymous in the eyes of the astronomical community. This isn't an oversight, it is a deliberate and somewhat controversial pause that speaks volumes about the complexities of discovery, classification, and the very human process of labeling the cosmos. The primary gatekeeper for this process is the International Astronomical Union, or IAU, the body responsible for assigning official designations to celestial bodies and their features. Their system is meticulously organized but moves with deliberate, sometimes frustrating, slowness. Before any feature can be named, the world itself must be officially classified and its defining characteristics thoroughly confirmed. Orcus occupies a peculiar bureaucratic gray area. It is widely accepted as a dwarf planet, but its official designation by the IAU remains that of a candidate dwarf planet, a provisional status it shares with other large Kuiper Belt objects like Salacia and Quaoar. This limbo state creates a procedural roadblock. Without a finalized classification, the process of approving names for its features cannot formally begin. The IAU prioritizes the most well-studied worlds, and with limited resources and a vast solar system to catalog, a distant candidate like Orcus simply hasn't risen to the top of the priority list, leaving its geography in a nameless purgatory. Beyond the bureaucracy, there is a more profound scientific reason for the hesitation, the fear of premature naming. The features we can currently resolve on Orcus are little more than blurry patches of light and dark. What we might interpret as a vast crater could, upon closer inspection from a future spacecraft, turn out to be a complex set of fractured canyons. That brilliant white spot we've discussed could be a single cryovolcanic dome or a sprawling plain composed of a dozen smaller features. Bestowing a permanent name on a geological formation based on such low-resolution data is a risky proposition. The astronomical community is still smarting from historical precedents where early, incorrect assumptions led to names that later became embarrassingly inaccurate. By waiting for higher resolution data, scientists avoid painting themselves into a corner, ensuring that when names are finally chosen, they accurately reflect the true nature of the geography they describe. This caution, while prudent, creates a frustrating lag between discovery and definition. The delay also stems from an ongoing, behind-the-scenes debate about what thematic naming convention should even be used. The IAU employs strict themes for different worlds. Pluto's features are named after underworld deities, mythologies, and pioneering explorers. Saturn's moon Titan draws from sacred or enchanted places in world folklore. For a world named Orcus, a Roman god of the underworld, the logical theme would be deities and figures related to the afterlife and the underworld from various global cultures. But this presents its own challenges. The names must be internationally recognizable, culturally sensitive, and not duplicate those used elsewhere. Researchers are likely deep in the process of compiling and vetting a suitable list, a scholarly effort that takes considerable time and careful negotiation to ensure the final selections are both meaningful and appropriate for a world that may one day be visited by human-made probes. Ultimately, the unnamed surface of Orcus serves as a silent testament to the fact that our exploration is still in its earliest stages. The lack of names is not an absence of knowledge, but an acknowledgement of how much we have yet to learn. It is a blank space on the map deliberately left blank, a promise to future generations of astronomers that the greatest discoveries about this enigmatic world, and the honor of officially naming them, still lie ahead, waiting for the day when our technology finally allows us to see its frozen surface in all its intricate and glorious detail. And now we arrive at a mystery of profound silence and absence, one that turns our attention from what is present around Orcus to what is conspicuously missing. The 24th great puzzle is not about the dwarf planet itself, but about the space it occupies. For a world of its substantial size, and one that has likely experienced a violent history of collisions, we would fully expect to find a surrounding debris field, a collection of dust, small rocks, and perhaps even a delicate ring system, the lingering evidence of past cataclysms. Yet, when we train our most sensitive instruments on the space around Orcus, we find nothing but empty void. This absence of a debris field is a deep and puzzling anomaly, a clean cosmic neighborhood that defies the chaotic reality of the Kuiper Belt and forces us to consider a history of either impeccable cleanliness or recent, sweeping disruption. This expectation of debris is not without foundation. We see these celestial litter fields throughout the solar system. The giant planets, with their powerful gravity, have intricate ring systems, vast collections of ice and rock that are the remnants of shattered moons or captured material. Even smaller bodies have their companions. The dwarf planet Haumea, for instance, is known to have a faint ring system, likely created by a past impact that ejected material into orbit. The presence of Orcus's large moon, Vanth, itself strongly suggests a violent past, most likely a giant impact. Such a colossal collision would have been unimaginably destructive, blasting millions of tons of debris into space. Where did all that material go? The fact that we see no sign of it today means that something must have happened to clean it up, and clean it up with astonishing efficiency. One compelling theory is that the very same moon we see today, Vanth, is responsible for the missing debris. In the immediate aftermath of the impact that created it, a vast and chaotic disk of shattered rock and ice would have circled Orcus. Over millions of years, Vanth, as the largest fragment, would have acted as a gravitational shepherd. Its orbit would have cleared out this primordial debris disk, either by gravitationally absorbing the smaller particles, sweeping them up like a cosmic vacuum cleaner, or by perturbing their orbits and flinging them away into space or down onto the surface of Orcus. This process, known as orbital clearance, is a standard part of moon formation, but for it to have been so utterly complete, leaving not even a wisp of dust behind, suggests that Vanth is an exceptionally efficient shepherd, perhaps due to its relatively large size and its specific orbital characteristics. Another fascinating possibility involves the subtle but persistent influence of Neptune. Orcus is locked in a precise gravitational resonance with the ice giant, a relationship that extends its influence far beyond a simple orbital rhythm. The periodic tugs from Neptune's gravity could be providing just enough perturbation to the space around Orcus to prevent any loose debris from settling into a stable, long-term orbit. Any small particle, a T Chinese letter ED, to form a ring, would have its orbit gradually altered by these external nudges until it either escaped the system entirely or collided with one of the main bodies. In this scenario, Neptune acts as a kind of cosmic groundskeeper, its distant gravity continuously sweeping the area around its resonant partner, maintaining a pristine emptiness that belies the violent history we suspect occurred there. We must also consider the possibility that the debris never had a chance to form in the first place due to the unique conditions of the impact that created Vanth. Computer simulations of giant impacts show that the outcome is highly dependent on the angle and velocity of the collision. A very energetic head-on impact might vaporize or eject most of the debris at such high velocity that it escapes the system completely, leaving behind little more than the two main bodies. Alternatively, an extremely low velocity grazing impact might be so gentle that it produces minimal debris to begin with. The current serene state of the Orcus-Vanth system, with its nearly circular orbit, might be the product of a freakishly perfect impact, one that was just violent enough to create a large moon, but just gentle enough to avoid making a mess. This would be a remarkably fortuitous event, but in a solar system of billions of objects, statistical miracles can and do happen. The most dramatic explanation, however, is that the debris field did exist but was very recently destroyed. Perhaps a rogue object from the Kuiper Belt, another large icy body, recently passed through the Orcus system on a chance trajectory. This interloper's gravity would have acted like a bull in a china shop, violently disrupting any delicate rings or clouds of debris, scattering them to the solar winds in a single catastrophic event. If this happened within the last few thousand years, which is a mere blink in astronomical terms, we would see the clean system we observe today with no trace of the recent chaos. The alternative recent event could be internal, a massive cryovolcanic eruption on Orcus itself, powerful enough to vent gases that acted like a pressure washer, pushing any lingering fine dust out of orbit. The absence of debris around Orcus is therefore a silent witness to its history, a void that speaks volumes about the powerful and efficient forces, both internal and external, that have shaped this distant world and the empty space it calls home. Yet for all its captivating intrigue, Orcus finds itself in a celestial waiting room, its mysteries languishing as more famous targets like Pluto, Europa, and Titan command the spotlight and the funding. This final, 25th mystery is perhaps the most terrestrial of all. Despite being a scientific goldmine, Orcus remains a surprisingly low priority for a dedicated future space mission, a puzzle of politics, engineering, and pure economics that keeps this enigmatic world at a distance. The reasons for this aren't a reflection of its scientific value, but a complex calculation of risk, reward, and the harsh realities of interstellar travel. Sending a probe into the outer solar system is one of the most ambitious and expensive endeavors humanity can undertake, and the path chosen must promise the greatest return for the investment. This creates a fierce competition among potential targets, and Orcus, for all its wonders, faces stiff challenges. The first and most formidable hurdle is simply its location. While Orcus resides in the Kuiper Belt, its specific orbital path is not as conveniently positioned as some other dwarf planets. A mission's travel time is dictated by the complex ballet of planetary alignments used for gravitational slingshots. A journey to Orcus could take several decades with current propulsion technology, a timescale that stretches beyond the career of the scientists who design the mission and tests the limits of political and public patience. In contrast, a mission to Jupiter's moon Europa or Saturn's moon Enceladus, while still a monumental task, can be achieved in a more palatable 5 to 10 years. This faster return on scientific investment is a powerful draw for space agencies that must justify their budgets to governments and taxpayers who are eager for discoveries within a human lifetime. The sheer distance to Orcus also presents immense technical challenges for communication. A signal from a probe near Pluto takes over 4 hours to reach Earth, and from Orcus, that delay is even longer, complicating real-time operation and requiring a spacecraft with incredible autonomous decision-making capabilities. Furthermore, Orcus suffers from a been there, done that perception in some scientific circles, however unfair that may be. The magnificent success of the New Horizons flyby of Pluto in 2015 provided a stunningly detailed look at a large, complex Kuiper Belt object. For many policymakers and even some researchers, the initial, overwhelming question was answered. We now know what a world like that looks like. This perspective overlooks the critical fact that Orcus is not simply another Pluto. Its unique composition, its potential internal heat, its bizarre moon, and its unresolved density all suggest it could be a completely different type of world, a prototype for a new class of object that would revolutionize our understanding of the Kuiper Belt's diversity. But overcoming the initial perception that it is merely a redundant target requires a concerted and persistent educational effort by its advocates within the scientific community. This advocacy is also hamstrung by the superior astrobiological potential of other worlds. The primary driving goal of modern planetary science is the search for life. While Orcus may have a subsurface ocean worlds like Europa and Enceladus are considered far more compelling candidates. They are closer. Their oceans are almost certainly in contact with a rocky seafloor, a key ingredient for life as we know it, and Enceladus has already been caught erupting its ocean contents into space, offering a tantalizingly easy way to sample it. Orcus's potential ocean is locked under a much thicker and colder shell of ice, making it far more difficult to detect or study remotely. In the brutal calculus of mission selection, a world that might whisper hints of life will almost always beat a world that whispers hints of unusual geology, even if those geological whispers are themselves revolutionary. Budgetary constraints form the final and perhaps most decisive barrier. There are only so many flagship-class missions, the multi-billion-dollar endeavors capable of exploring the outer solar system that any generation can fund. These projects are once-in-a-career events. The upcoming missions are already slated: Europa Clipper, the Dragonfly rotorcraft to Titan. The queue is long, and the line forms behind targets that have already spent decades building scientific consensus and political support. A mission to Orcus would be competing for funding and launch slots that won't become available again until the 2040s or beyond. In the meantime, smaller, cheaper missions might perform flybys, but without going into orbit or landing, they can only provide a fleeting glimpse, a handful of data points that would likely deepen the mysteries rather than solve them. So Orcus waits, a silent, frozen sphinx holding its secrets close. A testament to the fact that sometimes the greatest mysteries remain unsolved not because we lack curiosity, but because the universe, for all its vastness, is just out of reach. And so we reach the end of our journey, having traversed 25 of the most profound and compelling mysteries surrounding the distant dwarf planet Orcus. From its perfectly tuned orbital resonance with Neptune that defies billions of years of chaos, to the puzzling size and composition of its large moon Vanth, from the brilliant crystalline water ice that suggests a geologically active world to the confounding thermal emissions that hint at hidden internal heat, from the chaotic color variations and the possibility of cryovolcanic plains, eerie absence of any surrounding debris field, each enigma pulls us deeper into the story of this frozen sentinel at the edge of our solar system. We've grappled with its paradoxical density, its potentially recent resurfacing, its missing atmosphere, and its unique spectral signature that refuses to match any other known world. We've considered its possible origin as a scattered immigrant from the inner solar system, and pondered the influence of a hypothetical planet 9 on its path. Each mystery is a thread in a larger tapestry, one that challenges the very definition of a dead, frozen world and forces us to reconsider what is possible in the cold, dark reaches of our celestial backyard. Collectively, these puzzles present a monumental challenge to our current understanding of the outer solar system. Orcus is not merely a larger version of the smaller, inert rocks we once imagined populating the Kuiper Belt. It emerges instead as a complex, dynamic, and potentially differentiated world. Its mysteries suggest that geological activity is not confined to planets with strong internal heat or moons under intense gravitational stress. Instead, they point to a new paradigm where even modestly sized bodies, through a combination of residual formation heat, tidal interactions, and unique chemical processes, can remain surprisingly active over billions of years. This forces a complete re-evaluation of the Kuiper Belt itself, transforming it from a static museum of primordial relics into a region of dynamic and evolving worlds, each with its own unique history and potential for surprise. Orcus, in its silent, distant way, is teaching us that the processes of planetary science of volcanism, weather, and internal differentiation are universal, operating on slow, cold timescales we are only beginning to appreciate. This distant world, therefore, deserves far more attention from both the scientific community and space enthusiasts around the world. It is not a secondary target or a mere Pluto copy. It is a scientific goldmine, a prototype for a class of world we don't yet fully understand. A dedicated mission to Orcus would not be redundant. It would be revolutionary, capable of answering fundamental questions about the formation of our solar system, the diversity of geologic processes, and the potential for habitable environments in the most unlikely of places. Its story is a critical, yet missing, chapter in the biography of our cosmic neighborhood. Now we turn the conversation over to you. Which of these 25 mysteries captures your imagination the most? Does the origin of the large moon Vanth fascinate you, or are you drawn to the possibility of a hidden subsurface ocean? Perhaps the brilliant white spot or the chaotic color variations spark your curiosity. Share your thoughts in the comments below. Let's continue this exploration together and keep looking up, wondering about the secrets waiting to be uncovered in the deep, dark, and wonderfully mysterious frontier of our solar system.